This session, we're going to talk about renewable energy technologies, part 2. And so we talked a lot about biofuels and different ways to get access to renewable sources of energy last time. And now let's talk about ways to store them, control them, make decisions about them, use things like smart grids and machine learning. And so again, 3 10-minute presentations, 3 3-minute pitches. Judges, everybody's ready to go? Timer, we're all set. Okay, so our first 10-minute presentation will be by Mohammed Saad Arshad. Mohammed, the stage is yours.
Good afternoon, everyone. My name is Mohammed Saad Arshad, and I'm doing my master's in engineering management under the Department of Mechanical Engineering under the supervision of Dr. Pierre Martini. And my research involves around design and evaluation of electric bus fleet charging systems using hybrid energy storage solutions involving flywheels. So I'll start with explaining what basically a flywheel energy storage system is. This is basically a flywheel. What does a flywheel does? It stores energy. It uses electrical energy and stores energy in itself using in the form of a mechanical kinetic energy. So kinetic energy is basically the energy of a motion, and in this case, the spinning mass is this rotor which stores energy in it in the form of a kinetic energy. And whenever you need it, you can use the electric machine that is above it, which can act as a motor and a generator. And whenever you require the electric energy out of it, you can just extract it for that external purposes. You can charge this flywheel using biogrid or even the renewable energy sources like solar or wind or whatever. So the 4 major components of this flywheel energy storage systems are this rotor. So initially, the flywheel energy storage technology was evolving, and the rotors were made up of steel. But the disadvantage of steel is that it has, the RPM was pretty much lower in like range of 10,000s or whatever. So, and basically the rotational energy is directly proportional to the moment of inertia and angular velocity. So, with the development of technology, the rotors are now made up of composite materials, and they can made up of different rims of composite materials according to the application that we have. This rotor is also housed in vacuum, so that there's no effect of drag or there's no friction, so that it can keep on rotating, and whenever so it can store energy in it like for longer term, and you can extract the energy from it whenever you want it. So my project basically is City of Edmonton has around 900 plus diesel buses that are running on different routes all over the city. And the City of Edmonton has this initiative that they want to convert all the electric buses, all the diesel buses, to electric buses by 2030. So for that, it is of course a problem for a grid if there's a number like 900 plus buses being charged at different point of time. So it can put a load on EPCOR or whatever the supplying company can be, and it can even cause blackouts for the grid. So what this technology, the flywheel energy storage system, does is that it can store energy in itself, and whenever you require higher power, you can take a flywheel energy storage system into play and extract energy out of it. So we are basically looking for energy storage technologies that provides fast charging capabilities and of course high power, and that is why we are using the flywheels. There are of course mature technologies, other mature technologies as well. You are all aware of the electrochemical batteries, but flywheel has the advantage over the batteries is that it is like power dense, while the batteries are more energy dense. So what will happen eventually you'll be using grid or the renewable sources to even charge the flywheel energy storage system itself. But what happens is whenever you require energy from it, you just don't want to put load on the grid, right? So what you can do is when the energy is required, you can just use the energy being stored in the flywheel energy storage system, and extract the same amount of power and energy from the grid that is initially using for charging the flywheel. So what we want to do is that, in the current charging systems, we want to incorporate the flywheel energy storage system as well, so that because it provides high power charging capabilities. So moving on, so you would be worrying why? So batteries, we are already using batteries. So why are we supposed to use FESs? So there are superior aspects of FESs over the batteries. So as I've just mentioned, that FES has high power charging capabilities, and the other drawback, so you have to replace the batteries over time, but in this case, it has almost quasi-infinite charge and discharge cycles for the flywheel energy storage system. Apart from that, the batteries have depth of discharge limitations, but in this case, there's no depth of discharge limitations in case of FESs. Moving on, so So these are three manufacturers electric vehicles: Tesla, Nissan, and BMW i3 series. So what happens over the time the electric vehicle is being charged? So at the start of the charging, as you can see, you require higher power in every vehicle that is being charged, and the power requirements diminish over time. But like, how can grid provide such high powers initially, right? So that's the purpose of the basically the flywheel energy storage system. That initially, when high power is required, we can use flywheel energy storage system, and then eventually we can also use batteries as well. Moving on, so this is an example. Another example, with the difference between flywheel and the batteries is that, so as I just mentioned, that city of Edmonton is planning to convert its complete fleet to electric buses by 2030. So as a starter, they're getting 50 buses, electric buses via Proterra, which is an American manufacturer, by next year's summers. So let's say if we are charging, so the buses are being charged. So the capacity of the buses that they're getting is like the battery of the buses can store 660 kilowatt hour at most. So assume there's a 2 charge cycle per day, and then in the long run, in like 20 years, there would be like around 0.8 million cycles, right? In this case, if let's say, keeping it simple, if you're using a single FESS, you won't need to replace it. It won't require any maintenance. But in case of batteries, it has discharge limitations. So in case of batteries, you'll be replacing the batteries between 5 to 10 years, which involves cost, which of course involves environmental impact as well, because it has chemicals inside it. So moving on, so why do we want like these fast charging stations in Edmonton or anywhere around the world? The reason being, you can see the trend of the rising electric vehicles over time. So in 2013, there was like less than 0.5 million electric vehicles, and most of them were in United States. And you can see from 2013 up till 2017, they almost doubled every year. And by 2017, there were something above 3 million electric vehicles running around the road all over the world. And I'll show you the future outlook that we have, like how this EV market is going to revolve. So there are like two scenarios. So these figures were taken from International Energy Agency. Uh, you can see that between 2013, according to new policies scenario, the number of electric vehicles will increase something above 120 million around the world. But in case of, so there's this another scenario that is EV30 at the rate of 30, which means that by 2030, if we keep in mind that electric vehicle sales should be 30%, like all the vehicles will be replaced 30% by the electric vehicles, then the electric vehicles can increase something around 250 million electric vehicles. So that is an issue for the grid. So we need some stable energy storage technology for that. So these are the available charging levels that we have available at the moment. So as you can see, the DC fast charging stations are like very less around the world, 8.5%. And the advantage of DC fast charging stations is that it can charge an electric vehicle or an electric bus in minutes. As compared to the residential homes, you have to charge it overnight, like 8 hours plus, and they comprise 21.5%. And in case of parking in public buildings, they comprise most of it, and it takes around 2+ hours for charging. So in our case, so there are like 900 electric vehicles running on the road of city of Edmonton. So you cannot afford to charge them overnight, right? Because like they are running on different roads like repeatedly, and you have to charge them fast. So that's why we require more DC fast charging stations. So moving on, these are the current available charging solutions that we have. So we have different manufacturers around the world that are supplying high charging power. Most of them are battery based. So the maximum power that is being supplied by the Proterra, the manufacturer where the city of Edmonton is getting the buses from. So the maximum charge that's provided is 500 kilowatt, and the Tesla capacity at the moment is 145 kilowatt, and the other technologies lies between 500 and 145 kilowatt. So moving on, so as I initially mentioned that, so they'll be getting 2 buses this summer 2019, and the rest of them by next 2013, and the bus range in a complete charge would be 400 kilometers, and they will be charged using an overhead pantograph. So I'll give an example that how would we mitigate the load on the grid. So this is the typical route 4. Most of you would be taking it to coming to the university, the Capilano 4. So it starts from Levi's Farms and ends in Capilano Transit Center. It is around 40 kilometers long, and time to travel is approximately, depending upon the traffic, 80 minutes. So the buses that we are getting is, City of Edmonton is getting, is an operating efficiency of 1.17. So it requires 1.17 kilowatt of hour of energy per kilometer. And let's assume we have a charge window of 5 minutes. So we need a fast charging system, right? So what we can do in this case, so total energy required in the 5 minutes time span, if it has to run 40 kilometers, would be 47 kilowatt hour. So how do we get 47 kilowatt hour in 5 minutes? So the total power that would be required would be 564 kilowatt, but we cannot put that much load on the grid, right? So what we can do is, if we employ a flywheel of 423 kilowatt hour and take energy from the grid. So what I'm assuming is that after 15 minutes, the bus is being charged. So the complete duration of 20 minutes, the grid will be providing the same 141 kilowatt, and the total energy that would be required will be 11.75 kilowatt hour. And so the flywheel come into play, and you can see the range. So the flywheel 423 kilowatt, it's like thrice as compared to the Tesla that we had, like 120 kilowatt energy required. So that's why we require flywheel. The battery won't be able to do that in 5 minutes. That has been done up till now. So looking forward is that we have to, so this was a single route. We have to understand all the bus routes and of course the corresponding energy and power requirements. And of course then we have to determine the type, size and cost for both the technologies being used, the FESS and batteries, and so we have to optimize them as well, right? So we are also looking in the future work to develop a modeling framework that can be extended to other industrial and residential application as well. And that's all. Thank you.
Thanks very much, Sam. Sorry to be the guy looming with the tie again. That's just what I got to do. So we'll give the judges a second here to make their comments. Timers reset, and we will be joined next by Mohammed Rashidi.
Good afternoon, everyone. My name is Mohammed Rashidi. I'm postdoctoral fellow at the Department of Computing Science. The topic of my presentation is optimal control of distributed battery storage systems. The motivation of our work is what you see in the news. So a new renaissance for Europe, which is for solar generation, and also the reduction in fire risk by solar plus battery storage systems. Also, solar plus battery actually beats combined cycle gas as a conventional approach for energy generation. And also, we see that solar as a service is getting more popular. Solar as a service means that companies hire a rooftop of the customers and then install the solar panels to generate energy, and the customer may or may not purchase that. On the right figure, you see the exponential growth of solar PVs. PV means photovoltaic. And so as you see, the actually y-axis, which is logarithmic, and this means that the growth is exponentially increasing. And on the other hand, you see on the bottom one, we see that the cost of the equipment for solar generation is decreasing. So these all motivate us to design two learning-based control algorithms, which are formulated based on mixed integer linear programs, which is a non-convex optimization problem. We also developed a software program in Python, which is running on home gateways, which determines if the batteries should be charged or discharged for generating for energy, actually producing energy for the homes. We have also compared our algorithms with three baselines, and I will explain later. And finally, we investigated the economic feasibility of using this system for homes based on return on investment calculation and break-even point periods. It's called the system that we have developed as Energy Boost, so I will refer to this later. The system architecture is like this. We have a PV system or photovoltaic system here. We have a battery, we have home, we have also the grid, and all these are connected as we see in the figure. We have 2 meters which measure the amount of energy that is generated by PV and the amount of energy that is being sold or bought from the grid. So we have 2 options, right? And also we have a microinverter here which transforms the DC power generated by solar panel to AC power. We also have EMU, or Energy Management Unit, which actually plays the role of an actuator. This EMU actually charges or discharges battery by transforming the AC and DC power together. And also we have some data from internet that are actually being used for our system, which is here. So this data actually is the pricing or historical data, and also the actual real-time values for PV generation that are being injected to here, and then this calculates if the battery should be charged or discharged. So also we have this system structure. We might have some limitations, like the battery cannot be charged more than its capacity, and the solar energy may not be produced whenever we have the cloudy day, or electricity price may change over the day. So based on these limitations, we may need to predict to have higher performance control, and to predict data, we need to have a model. So we have two different types of models, physics-based models and data-driven models. So the physics-based models are for battery and solar inverter that are coming from literature. But in order to predict the home demand, also PV generation, we use data-driven modeling based on the historical data. So since we have historical data, we might have many, many features being kind of effective for our predictions. In order to find the most relevant features, we use an algorithm called an OFS score. And then by finding their most relevant features, we tried a variety of modeling techniques to find which one has the minimum or causes the minimum root mean square error for our next 24-hour prediction. And then by having the model, we could design learning-based controllers. We can have different type of learning-based controllers. One of them that seems to be obvious is day-ahead scheduling. Means that you use a model to predict the next 24 hours, and then relying on that, you actually calculate when to charge and discharge battery, and also when to have consumptions. This has a drawback which heavily relies on the model, which is in an offline fashion. In order to improve that, we can have model period control, which relies on a model in an online fashion, means that the model is getting updated in every time slot that we have new measurements. But it's still relying on actually the modeling accuracy. And the other one is model-free control, which relies on reinforcement learning. Reinforcement learning actually learns from the interactions with the environment or physical system. However, it requires to actually have some explorations. This exploration may be out of the scope of this physical system and may damage that. So we may need to design a simulator to play the role of that physical system. However, this again relies on modeling, and so may have some inaccuracies. In this work, we have relied on these two algorithms, and then designed them for controlling battery charge and discharge. So as I said, model predictive control so is one of the control algorithms. In model predictive control, we have desired outputs, and based on the desired outputs and our model, we can find what control inputs can lead us to those control outputs. To do that, we need to minimize or optimize an objective function, and here we are minimizing the objective function, and that is the amount of energy that we are purchasing from the grid. So by minimizing that, and also under some constraints, we can find the control policies that we may need for our control algorithms. The other one is reinforcement learning. So in reinforcement learning, as I said, instead of taking the expected values or the average values, we may take samples from distributions. So it's kind of a stochastic optimization that has advantage. However, actually it has to maximize the expected cumulative rewards. And in order to find which policy is the best one, so we have to use an actor to take the policy, and then a critic to evaluate that. So this is the reinforcement learning. Based on these control algorithms, we have tried different simulation scenarios based on different sizes of battery and PV system, also pricing schemes that may exist. And also we have used 3 baselines to evaluate our algorithms. Those baselines are Oracle, which is the best policy that we can theoretically obtain. The other one is rule-based controller that you see on the right side, which is constant over the time, doesn't change. And also we may use those features to actually directly predict the control actions. Now, we have used data for 70 homes in the US. This result is for only one home, which is randomly selected, and you see that model predictive control is closely tracking the optimal one, and it's outperforming the other control algorithms. We have also evaluated the control policy for all the homes, all 70 homes, and then we plotted the electricity bill during the year for all of them. And we see that here, actually MPC for all of the solar tariffs is outperforming. Solar tariff is the tariff that is used for selling the energy back to the grid. So as we see here, if we have higher solar tariff, the actually bill would be reduced. And finally, we also evaluated the control policies based on the payback period. We see that MPC always has less payback period compared to RBC, the rule-based controller, and also higher solar tariff causes less actually payback. And finally, we can say that we have evaluated different control policies and found that MPC outperforms other ones, and also MPC reduces the payback period compared with the RBC or rule-based controller by 44 months. And also some certain battery sizes could be profitable, and also control time scale may not be very important for finding the control actions. Yeah, thank you.
Thank you very much, Mohammed. So one more 10-minute presentation before we move into 3-minute pitches for this session. And so I'll let the judges scribble their notes away. Timer's resetting. And Mohammed is getting ready. Waiting for the thumbs ups. Got one from John. Okay, everybody's good? Take it away.
Hello, everyone. Before I start my presentation, I have a question for you. What is your familiarity with risk management process? Like, you can raise your hand if you have experience. Okay, so in this presentation, I will give you a little information about the first component of the risk management process, which is risk identification. A risk management process is a generic process that can apply to any type of any project or any product. So in this case, I will apply the risk management process in wind farm project construction. So I will introduce the topic, and then what is the problem that we are facing in this project. So what is the research objective and research methodology, and then the result and future work. Canada and the world moving toward the usage of renewable, multiple sources of renewable energy infrastructure, such as the wind and solar farms. Two reasons for that. The first one is to reduce the negative effect for the fuel combustion. The second reason is to pile up the limited stock for the fossil fuel to make it sustainable for the other generations. As we can see from the figure that the wind energy is growing rapidly in Canada. From 2008 and 2018, the total installed capacity is increased 12 gigawatt for wind energy, and that represents 60% of the total energy production in Canada. So the federal and provincial government continuously supports the development of renewable energy infrastructure. And in Alberta, there is a program which is a renewable electricity program that's already launched, and it's aimed to add 5,000 megawatt of renewable energy by 2030. And in this program, the wind farm is the main component and or main type of the renewable energy sources. The problem statement is with increased fund and increased development of renewable energy infrastructure, and especially wind farm projects. In order to guarantee the successful completion of this project, so we have to properly assess and identify the risk factors that are affecting the construction of these projects. And wind farm project it's a unique type of construction project that has its own risk factors, so it has to adequately addressed. So the construction phase of the wind farm project represents 25% of the total cost for developing a wind farm project. So it has an importance, and it should be adequately addressed. So the research objective is two objectives. The first one is to comprehensively identify the risk factor affecting a wind farm project. And the next one is to prioritize these factors according to the different criteria. So the research methodology is the first thing we have to identify the risk factors, the potential factors. We started by reviewing the literature review and collecting the initial factors, and then we have to introduce this factor and evaluate it according to Canadian perspective. So we introduce it to the Canadian companies to evaluate the factors, and then we use the evaluation from the companies to rank these factors according to the fuzzy topsis analysis technique. And the output for the process will be the ranked risk factors, so we know which factors that we have to give more focus and in our analysis. I started with analyzing the literature review, and I was able to extract the initial factors that affecting the construction of a wind farm project. This factor is divided into internal and external factors. The internal factors that coming from the project itself, and the external factors coming from the surrounding environment for the project. So the external could be local or global. The local one is coming from the country itself. The global one is from worldwide. So in the local, we have financial, legal, social, political, and environmental sources for the risk factors. The same for internal factors. It could be coming from the site characteristics or from the management-related factor or financial or technical factors. So in total, we have 31 factors that affecting the construction of a wind farm project. So the next step is to formalize the questionnaire and introduce it to the partners. So for the evaluation of a risk factor, we have to identify the impact and the probability of occurrence for a risk factors. So the impact will be identified according to the cost impact, the time impact, the quality, and the safety impact for each risk factor. That's why it is a multi-criteria problem. That's why we use fuzzy topsis. And for each factor, it has only one, like the probability is one value. So we collect all this information for all the experts and we combine it, and then the application of fuzzy topsis can be conducted. At the current stage, we finalized the questionnaire, and we are expecting to get to distribute it and collect the result by in July. Yeah, thank you very much for your attention.
Thank you very much, sir. I'm always jealous of this fuzzy logic, this incredibly powerful tool. Back when I was studying history, if I used fuzzy logic, it didn't get me anywhere. Very different definition of the term. So we're ready to start moving over to our 3-minute theses. I'll let our judges get prepped. Sarah will be up first, so we'll get her standing by.
Recently, the idea of using renewable energy on large scale has drawn a lot of attention. Solar panels like the ones that we have on campus that you can see in this picture, and also micro wind turbines have become affordable and efficient to use in both commercial and residential buildings. We want to solve the problem of complex and large-scale energy systems. Right now, with all these distributed energy sources and all these different complex components of the energy system, it is very hard to use the traditional centralized management systems to manage this complex ecosystem. We need a new distributed, dependable solution. In our research group, we are trying to use distributed ledger technology to solve the problem of complex distributed energy systems. Distributed ledger technology is mainly known for its anonymous network. One example is Bitcoin. Bitcoin is known for its anonymous peer-to-peer network, which is not controlled by any central authority. However, Bitcoin has a main problem. It has the main problem of performance. It is not as efficient as we need. It takes about 10 minutes for a transaction to be completed in this network. However, this is not even close to what we need for the distributed energy resources. That is why we are using a new distributed ledger that is called IOTA. IOTA is explicitly designed for IoT platforms and is more scalable compared to the traditional blockchains. We are focusing on the performance evaluation of this technology, and we want to optimize and tune this technology for different IoT scenarios, including but not limited to distributed energy resources. The result of our research would then be an efficient distributed ledger that can be used for managing energy systems in the future smart cities. Thank you.
Thank you very much, Sarah. And in fine time, our next 3-minute pitch comes from Evandro de Souza. Let's just give a second for the judges to finish their remarks. Reset the clock.
The title of my presentation is Co-Simulation Architecture for Smart Grid. In this presentation, I want to answer two relevant questions. First one, what is co-simulation? And second, why is it relevant for smart grid applications? I'm going to give an example to you to understand that. Imagine that you need to allocate power in an EV charging station. In order to create the control algorithm for this station, you need to have some information, such as you need to know when the EV arrives at the charging station. You need to know some thing about mobility. Also, you need to know how much solar energy is available for the charging. Also, you need to, when the vehicle arrives, you need to inform the service provider how much energy you need. Also, you need to, when you have the power to allocate to this vehicle, you need to know if this is going to create an overload or a voltage drop in the transmission power. You can see that you have several domains, and if you want to have a good view what is going to happen, you need to create a co-simulation for this thing, because you have different domains that you need to simulate in isolation. This is what is traditionally is done, but now you need to make all of them work as a single entity. What's the challenge for this work? First, when you need to combine several different simulators, you need to take into account that they were created with different paradigms. Also, they were created with different data models, and they were designed for different time scale. And now you need to make all of them work as a single entity, okay, to produce a high fidelity simulation. So this is the challenge that we have for this work. How can co-simulation framework helps? Well, they help people and projects that need multiple domains, such as designing grid control algorithms, as I presented before, when people need to do a grid cybersecurity analysis. And one important one is that when you need to do hardware in the loop simulation. So what the outcome of this project is to provide a tool that provides an accurate, concise, and complete view of future smart grid applications. Thank you.
Thank you very much, Evandro. So again, we'll give the judges just a second. Aaron's already on his way up. Reset the clock. This is Aaron Kirky, and he is going to give us 3 minutes.
Today, I'd like to talk to you about something called design of experiment and machine learning. And when these two things are coupled together, they've completely reinvented the way that we optimize solar cells. So just a little bit of context. In 2010, the world used 16 terawatts of power. And by 2050, conservative estimates that take into account unprecedented energy conservation expect that this value will double, which means we need to find a way to produce 16 trillion more watts, or not 16, but 160 billion 100-watt light bulbs burning 24/7. Good question is, how do we do this? So in this figure, on the right side, we have the the known reserves of non-renewable energy sources, and on the left side we have the potential power generated per year for non-renewable sources. And this big yellow circle, the elephant in the room, is the energy produced by the sun every year. And so it seems like this would be a wise place to start with meeting this energy demand. This is why one of the focuses in our research group is on organic photovoltaics, or OPVs for short. These devices can be printed with high throughput manufacturing techniques like roll-to-roll printing, the same way newspapers are made, and the resulting devices are extremely lightweight and flexible. However, they consist of very complex layered architectures, and each of these layers needs to be optimized very finely to get a high performance device. And producing every possible device is simply not possible. So say, for example, you had 8 different processing parameters, things like concentration or temperature, and you wanted to look at 4 different levels for each of these processing parameters. You would have a possibility of making over 65,000 possible devices. And assuming each device takes 2 hours to make, this would take about 9 years to do. I personally don't plan on being here for 9 years, so hopefully there's a better way of doing this. So how should we go about optimizing OPVs? So typically in academia, what happens is you start with a point from, say, literature, or maybe the most convenient point. And I would liken this, the best analogy to use in this scenario would be to find the point of highest elevation in this auditorium. So if you were to start, academia starts with a point that is maybe most convenient, and that point could be right here. And it takes, they optimize one step at a time, using one variable at a time optimization. And I would liken that to trying to find the highest point in this auditorium with the lights off and nothing but a flashlight. And so I could take a step forward and maybe a step to the left. How long would it take until I found the highest point in this auditorium? Instead, using design of experiment, we can strategically place floodlights about the room, and then using this data and machine learning, we can reconstruct a map of the areas of highest elevation throughout the room. This is what our approach allows us to do. This figure is from a paper we published last year in collaboration with the MAR group. On the left is a figure that shows the results of some design of experiment research we did. And the results show that with only 32 experiments, we were able to produce a cell that performed 25% better than anything found in literature. And something I would really like to highlight is this technique for quickly optimizing systems is not confined to organic photovoltaics. And so this is something that could be applied to almost any system for any application. And I wonder what caliber of future energy system could we be building with this approach? Thank you.
Thank you, Aaron. One of the tough parts of being the MC today is I'm not allowed to provide any sort of things that could bias the panel, so plug your ears, folks. But it's interesting because the design of experiments, the machine learning stuff that Aaron was just talking about, last year at this event, it was machine learning groups from the solar group and from the carbon capture and storage group who actually found each other in the poster competition and then ended up doing machine learning workshops over the summer. It was a great opportunity for different groups from different parts of our program to talk to each other. So again, this is one of the reasons why in our poster competition you are not allowed to vote for somebody in your own strategic area. We're trying to encourage more of those conversations. That brings us to the close of this session, and we're running a little bit ahead of time once again. Just to confirm, we reconvene here at 3:30. A note, before the last break, I told you that it would be the blue posters last time. There were the blue numbers who were at the posters. I was completely wrong. Go figure, it's me. It was the green posters last time. It's going to be the blue ones this time. So the renewable energy folks will be out there. Please check out those posters. Get ready to vote. This is not the last break for voting on posters. After the next session, there will be one more break. And again, if you're waiting to find out if you won, whether you're a presenter or whether you're doing a poster, that's at the end of our very last session. So hang in there. Coming soon. All right, folks, so we reconvene here at 3:30.